Hello, in this video I'm going to continue exploring conics, specifically hyperbolas. And so I typed in a quick Google search for hyperbolas in the real world, and I came up with a whole bunch of pictures, a lot of architecture, some design, a little bit of stitching on baseballs and basketballs, a guitar. There's also some gears, a little bit of projectile motion, gravity, and trajectory in space. Again, more architecture, some maybe fluid dynamics. What else do we have here? Main idea is that there are a lot of applications. We've got some inverse relationships, like maybe supply and demand, or temperature and pressure. And remember, this all comes from splitting a double cone with a plane. And so this might seem like magic almost, but if somebody walks into a mathematics classroom or encounters math these days and takes a look at this on the board, this monstrosity, and then this bunch of letters and numbers next to it and says, well, oh my gosh, that's just ridiculous, it's so boring, has absolutely no value, it's not important to me, what am I ever going to do with that? Well, then we should first actually make a value judgment on that and say that is outdated. You know, if you want to own a telephone, or what shouldn't be called a telephone, just a mobile device, if you want to participate in any sort of modern technology, including just simple television and things, then math is for you, and it is definitely part of your daily life. Whereas 1,000 years ago in Europe, the governmental, religious, political, military leaders of the time actually outlawed this zero-based algebra because, well, A, I think it threatened their superiority over all things, because using this algebra and other related physics and mathematics, people determined that the sun did not revolve around the earth, and, well, that was obviously earth-shattering and crumbling, led to a disintegration of the worldview. But it is true that 1,000 years ago or so, all this stuff was merely theoretical and on paper, and maybe it didn't have much of a place in the real world, which was basically just about subsistence and survival. And throughout the centuries, there was actually very little direct, explicit, practical application of proof showing that this stuff, these numbers and letters and equal signs and things on paper, had any bearing on relationships between objects or energies in the real world. But in fact, in the past 100 years, that barrier has been thoroughly demolished. That all of our modern technologies, and from automotive to electronic and beyond, basically everything we use, unless it was handmade, and even in those cases, the tools which make the handmade things rely upon physics and mathematics. We have all of this proof that these paper-based ramblings, what it might have seemed like 500, 1,000 years ago, are in fact just a different way of expressing ideas and condensing very abstract and encoding and speaking about, in a way, these very complex phenomena which occur in nature. And without mathematics, we wouldn't be able to understand things. Without then representing them in graphical and other forms, we wouldn't be able to use them in labs and then experiment with different materials and, again, use them to discover things about the natural world which perhaps seem trivial to some, but in fact, if we're using money and participating in economy and driving in cars and using phones and computers and things, then in fact, these are very relevant. So next time you look at that math and say it's boring, I say, well, then that's just a state of mind. It's probably, it might even be evolutionary, that for thousands of years, our focus as humans was on survival, and, well, sitting in a dimly lit room by candlelight or whatever, scribbling on papers, did not ensure the survival of oneself or one's lineage. However, today it's really quite different. So evolve, adapt, change, and rise above the ranks of those who came before us. There's nothing wrong with that. Anyway, on to the hyperbola. we can see that it is a set of points where the difference between a point on a curve and a focus, and the point on that curve and the other focus, and the opposing curve are always equal. You can see these magnitudes F and PG are growing, but the difference between the two is staying the same no matter where the hyperbola curve lies, no matter how flat or steep the concavity, convexity is, no matter what the eccentricity is. You can see the distance, the difference between these two is always the same. And so we've got some vocabulary here, big schematic of axes and vertices and foci and directrices, directri, directrices, asymptotes, etc. And we can draw a box then which barely touches that vertex extending to the asymptote, and then we can make a right turn perpendicular to the next parallel line which touches that vertex and then extends to the asymptote again. And so we get our standard form, x minus x naught quantity squared over a squared, where a is that distance between the asymptote touching the vertex and going to the next asymptote, minus y naught quantity squared over b squared, where b is that distance along the x-axis between the two asymptotes and the vertices. And then x naught, y naught is the center here where all the axes and asymptotes crisscross. And so I've typed this into Geogebra, got the same thing, and Geogebra automatically converted it to decimal form and got rid of the coefficient of y. That's just how the program is structured. So it did that automatically. We've got our a is 3 because 3 squared is 9, our b is 2 because 2 squared is 4, our x naught is 2, our y naught is 1, and so we can see then our center point f here is 2, 1, or x naught, y naught. We can see our axes are x equals 2 and y equals 1, right? And then we can find our vertices. Again, vertices and all of this stuff is actually pretty simple using Geogebra, because all we have to do is type in directrix or vertex or focus or asymptote or whatever it is that we're looking for, right? Intersections of different lines. Focus, again, vertex. Right, so a lot of this stuff is automated for us, but that doesn't mean we shouldn't try to triangulate and supplement our technology-based learning, our inductive learning, with more deductive and just other types of representation. So looking at the rules here, or the formulas from byjus.com, which is available on dozens and hundreds and thousands of sites, I'm sure. Major axis minus minor axis found, eccentricity, we'll come back to that. Our vertex, we found that. Our foci, x naught plus the square root of a squared plus b squared colon y naught. So x naught is 3, square root of a squared plus b squared is the square root of 13. And so that's going to be 3.61 roughly. So we're going to be at x naught, which is again 3 plus 3.61, 3 minus 3.61 for our vertices. Sorry, x naught is 2, excuse me. X naught, I was thinking about a, sorry. X naught is 2, so 2 plus 3.61. There we get our focus on the first one. Finding the foci, 2 minus 3.61. Negative 1.61, again, just labeling focus, typing in focus, C, focus, and then the label of the conic will do it automatically here on Geogebra. So those are the foci, that's easy enough. Vertex, A, Y naught, negative A, Y naught. Let's have a look back here. A, Y naught. And so that's a distance from the center point here. So it's 2 minus 3, which is negative 1, and then 2 plus 3, which is 5. So that checks out. Now let's look at our asymptotes. Y equals, there are 2 of them. You can see 2 of them. Now the asymptote is the line which forms the limit of the parabola as we reach infinity. So of the hyperbola. The hyperbola curves will never actually touch these asymptotes, but they will approach them as x trends to infinity. Remember, from limits, that's what limits are. Asymptotes are, in fact, limits. Right, so our equation of our asymptote are up here, and again, all I had to do is type asymptote, and it gave me both of them. But if I wanted to figure them out by hand, I would use these 2 equations. Y equals y naught minus, plus or minus, b over ax plus or minus b over ax naught. Looking at what I've done here in my notes already, got a, b, y, x naught, y naught. And so again, that's our equation of the one asymptote, y naught minus b over ax plus b over ax naught. Just going to substitute. Y naught is 1, and then b over a is 2/3, and x naught is 2. We're going to combine like terms. 1 minus 2/3 times 2 is 1 plus 2/3 over 2 is 1 plus 4/3. 1 in fraction form is 3/3, so 3 plus 4 is 7/3. Here we get 7/3 minus 2/3 x. And when we look back at GeoGebra, it's in a different format here. We're going to be looking at this one with the 7. And so let's do a little bit of algebra just to check here. We get 2x minus 3y equals negative 7. Again, that's from our equation here on GeoGebra. We're going to move that 3y over to the other side, move the 7 over to the other side. We get 3y equals 7 minus 2x. Divide by the coefficient of y. We get 7 over 3 minus 2/3 x equals y, which is exactly as we got here. So that checks out. GeoGebra and technology just do it faster, that's all. Then finally, the last part here, we're looking at the directrix. We've got 2 directrixes. And very similar to a parabola, the directrix plays a part in determining the graph, or let's see, what does the directrix do? It's a straight line that's used in generating the curve. It can also be defined as the line from which the hyperbola curves away. Right? The line is perpendicular to the axis of symmetry. We could explain it a little bit more, I'm sure. Directrix, fixed straight line. Okay, so any branch of the hyperbola can also be defined as a curve where the distance is from any point of a fixed straight line, same as a hyperbola. So these are basically like facing hyperbolas, right? Or like one person's, a northbound Zach's stuck in his tracks and a southbound Zach's stuck in his tracks. These are their 2 eyeballs staring at one another, if you're down with that. And so the distance from the focus to the directrix is the same no matter where you are, just like we saw in the hyperbola. Right? To find the equation of the directrix, all you have to do is type in directrix, and we get x equals negative 0.5 and x equals 4.5. I think those are approximations. I could change the rounding and come up with something slightly different. Let's look at a more precise measure here. X equals plus or minus a squared over the square root of a squared plus b squared. And so we could also say that, I'll get back, I'll do this one second. We could also say that a squared is equal to 9. So 9 over the square root of a squared plus b squared is 9 over square root of 13. I believe that is the square root of 13, but we'll just do 9 divided by the square root of 13 is 2.496, right, or 2.5. Again, I would just have to change the rounding here. On GeoGebra, that's correct. And it's 2.5 from the center line, right? So 2 plus 2.5 is 4.5. 2 minus 2.5, again, roughly, is negative 0.5. It's actually negative 0.496 and 4.496, right, where we're we're not rounding quite the same. We could also say that d is the distance from the center at which the directrix lies, and then d equals a squared over c, where c is the distance of the focus from the center. Now let's look at how far the focus is from the center. So f and d are, did I already calculate it? Nope. Let's find f and d. Not in there. Here we are. Find the distance from f and d, and we get 3.61, which is precisely what the square root of 13 was, right? Rounded, of course. And finally, again, so the distance from any point on a hyperbola to the opposing focus, the difference between the distances between the foci, are going to be equal no matter where on the hyperbola those 2 points are. And so I've calculated those already. So we've got EC is the distance between the point and this focus. ED is the distance between this point and that focus. And then over here, ED minus EC is 6. And we can see as the distances move, we've got E is moving, we're going to find ED and EC are changing, but then B is staying the same. So that the difference between those two stays the same, just as advertised. Right? And then we could also find that if we wanted to measure from E to the directrix, and then E to the focus, these should also stay the same no matter where we are. Going back to directrix, we fixed the ratio is always the same, sorry. And so again, if we wanted to draw, let's draw a perpendicular line from here to here. And we'll put a point on that intersection, and then we'll measure that intersection from here to here. And then we're going to say the ratio, we're going to say EC divided by EI, and we get EC divided by EI. We get n equals 1.2, so that ratio should stay the same. Go back here to the pointer, move stuff around, and we see that EI and EC, the distance changes, but the ratio n over here stays the same. So as advertised, all points on the hyperbola are equidistant from the sorry, to phrase this, the difference between the lines or segments from any point on the hyperbola to each of the foci is always the same, and the ratio of the distance between the point and the directrix and the point and the focus always remains the same. So these are slightly different than what we saw with parabolas, but following that same basic trend since they are conics. Okay, so you can, again, download Geogebra and explore using the internet, using technology, using just some pencil and paper as people did for so long, which in fact led to all of this fancy technology that we had today. Somebody had to do the math first. Or you could, stay stuck in the past and just refuse to change along with the rest of the world by saying math is boring and it has absolutely no relationship to the real world. However, in doing so, you will be denying reality. So while all of the friends and things and all of the social media might say it's cool to be a math illiterate, I think there is sufficient argument to suggest that is not correct. Okay, thank you.